Hey everyone, and welcome. Have you ever looked at a bag of cement and wondered what the M in M25 concrete really means? Or how engineers are so confident that a massive skyscraper won't just crumble? Well, you're in exactly the right place. In this explainer, we're going to break down the compressive strength of concrete and the statistical magic behind it. And trust me, these are concepts that are absolutely critical for your SSC JE exams. Just think about that for a second. Every single building, every bridge, it all relies on concrete doing its job, day in and day out. But how do we get from a simple pile of cement, sand and stone, to a number, a value we can confidently plug into our designs? That's the big question we're going to tackle today.
So here's our roadmap. First, we'll nail down what concrete strength even is. Then, we'll see how it's actually tested in a lab. But the real game changer is understanding characteristic strength, and that's where the statistics come in. We'll look at the math, see how the official IS 456 code puts it all into practice, and we'll wrap up with the exact points you need to memorize for the exam.
All right, let's start with the absolute foundation of this topic. When engineers and designers talk about the strength of concrete, what property are they actually talking about?
It's all about compression. You see, concrete is an absolute beast when you try to squeeze it, but it's pretty weak if you try to pull it apart. So its ability to resist those pushing forces, those axial loads, that's its compressive strength. And this one single property is, without a doubt, the #1 metric we rely on for all of our design calculations and for quality control on site. So, how do we actually measure this compressive strength? I mean, you can't just look at it and know. We need a standardized, repeatable process to get a number we can trust. And that brings us to the physical test. And the official rulebook for this entire procedure is Indian Standard 516. You can think of this code as the law when it comes to strength testing. It dictates every single tiny detail: how you have to mix the concrete for the sample, the exact dimensions of the mold, the temperature of the water for curing and for how long, and precisely how to operate the machine that crushes it. Now, why is this so important? It's all about consistency. It ensures that a test done in Mumbai gives the exact same type of result as a test done in Delhi. It removes all the other variables, so we are purely measuring the inherent strength of the concrete mix itself. And that consistency is absolutely non-negotiable for safety. The process itself is pretty straightforward. First up, a standard 150 millimeter cube is cast from a fresh batch of concrete right on the construction site. Next, this cube is submerged in a curing tank, usually filled with water, for a full 28 days. This allows the concrete to hydrate and gain its proper design strength. And finally, that cured cube is placed in a big machine called a compression testing machine, or CTM, and a gradually increasing load is applied to the top and bottom until it fails, until it crushes. The force at which it breaks is what gives us our compressive strength value.
Now here's where things get really interesting. In India, we use a cube. In other places, like the US, they use a taller cylinder. You'd think they would give the same result, but they don't. The cube actually gives a higher strength reading. And the reason for this is something called frictional restraint. Imagine this. The steel plates of the testing machine are pressing down on the cube. As they squeeze it, they also grip the top and bottom surfaces, preventing the concrete from expanding outwards like it naturally wants to. This confinement, this gripping action, artificially adds to its strength. But in the taller cylinder, the middle section is far enough away from those steel plates. It isn't affected by that friction, so it fails in a state of pure, simple compression, which gives a lower, and you could argue, a more realistic measure of the concrete's true strength.
And this difference leads us to a critical conversion factor that you absolutely positively must remember for your exams. The cylinder strength is taken as approximately 0.8 times the cube strength. This isn't just a random number. It's the correction factor that directly accounts for that extra artificial strength the cube gets from the frictional restraint of the machine. So remember this number, 0.8. It's a big one. Okay, so we know how to test one single cube. But here's the thing. Concrete is inherently variable. Not every cube from the same batch will have the exact same strength. So how do we come up with a single, reliable strength value for our design, like M25? This is where we have to move away from a single physical test and into the world of statistics.
And here it is. This is the official definition of characteristic compressive strength, or FCK, straight out of IS 456-2000. You need to memorize this sentence word for word. It is one of the most frequently asked definitions in exams. The strength below which not more than 5% of the test results are expected to fall. Notice, it's not the average strength. It's a kind of guaranteed minimum strength, but with a small, statistically acceptable chance of failure.
Let's make that super practical. What does it actually mean?
Well, if you have M25 concrete, its characteristic strength, its FCK, is 25 newtons per square millimeter. According to that definition, if you were to make and test 100 cubes of this concrete, we are statistically accepting that it's okay for up to 5 of those cubes to fail below 25. But, and this is the important part, the other 95 of them must pass. They have to be at or above 25. This probabilistic way of thinking is really at the core of modern, safe structural design.
Okay, to really, truly get that 5% rule, we need to dive into the statistics that power the whole thing. I'm not kidding, this next section is probably the most important part of this entire explainer, so let's focus in.
So when you test dozens or even hundreds of concrete cubes, the results don't just land all over the place. They follow a very predictable pattern called a normal distribution, which we see as a classic bell-shaped curve. Right at the very center, the highest peak of that curve, is the mean strength, or FM. This is just the simple average of all your test results. But the most crucial term for us, the one that tells us about quality, is the standard deviation, which we call sigma, or sigma. This number tells you how spread out your test results are. A small sigma means all your results are clustered really tightly around the average. That makes a tall, skinny bell curve, and it's a sign of excellent, consistent quality control. A large sigma means your results are all over the place. That gives you a short, wide curve, and it's a huge red flag for poor quality control.
And all of this comes together in the single most important formula for this talk. Let's really break this down piece by piece. We start with FM, the mean, the average strength of our concrete. That's our starting point. But wait, we can't use the average for our design strength, can we? Of course not. That would mean 50% of our concrete is actually weaker than what we designed for. That's way too risky. So we have to subtract a penalty, a safety margin. And what determines the size of that penalty? It's our consistency, which is measured by sigma, the standard deviation. If your quality control is sloppy and inconsistent, you have a big sigma, so you get a big penalty. If your work is tight and consistent, you have a small sigma, and you get a smaller penalty. And that is where the 1.65 comes in. It is the specific statistical number that corresponds to our 5% failure limit. So the formula FCK equals FM minus 1.65 sigma is basically telling a story. Our guaranteed strength, FCK, is equal to our average strength, FM, minus a penalty for being inconsistent, 1.65 sigma. This is how we mathematically enforce quality control.
So where on earth did that magic number 1.65 come from? It's not arbitrary at all. It comes directly from the mathematics of the normal distribution curve. This K factor, as it's called, is directly tied to the percentage of results you're willing to let fail. If we were okay with 10% of our concrete failing, we would use a K factor of 1.27. But IS 456 is strict. It mandates a maximum of 5% failures. And the statistical constant that corresponds to that 5% threshold on a normal distribution curve is precisely 1.65. This number is what directly connects our formula to the code's official definition.
Okay, that's some pretty heavy theory. But how does this actually work in the real world? I mean, imagine you're a junior engineer on a brand new project. You don't have 30 past test results to calculate your own standard deviation. So what do? How do you design your concrete mix? Well, lucky for us, IS 456 provides the answer with this incredibly important table. When you don't have enough of your own historical data, the code gives you an assumed standard deviation to use in your calculations. For the lower grades, M10 and M15, you use a sigma of 3.5. Now, for the really common grades that you'll use all the time, M20 and M25, the code says to assume a standard deviation of 4.0. And then, as you get into the higher strength concretes, from M30 all the way to M50, the code recognizes that these can be trickier to control, so it assigns a higher assumed sigma of 5.0. This table allows you to calculate the target mean strength that your concrete plant needs to aim for to make sure you actually meet the required characteristic strength on site. It's a lifesaver. Woo! We have covered a lot of ground. Now let's bring it all home. Let's distill everything we've talked about down to the absolute essentials that you are most likely to see on your SSC JE exam. Okay, here we go. Number 1, you have got to be able to recite the definition of FCK from IS 546 by heart. That whole 5% rule is pure gold for objective questions. Number 2, that formula, FCK equals FM minus 1.65 sigma. It's not just letters and numbers. It's a story about quality control. Make sure you understand it inside and out. And number 3, a little bit of memorization here will go a long way. Know the key assumed standard deviation values, especially 4.0 for M20 and M25 and 5.0 for M30. These 3 points are the highest yield information you can have for your preparation. So there you have it. We've gone from a simple question about strength all the way to the statistical heart of modern concrete quality control. This framework, this way of thinking, is what allows us to build incredible structures with confidence. The theory is now yours. The next step is to get out there, practice, apply it to problems, and absolutely master it for your future career and, of course, for your upcoming exam. Best of luck.